Greetings, everyone. Time to continue what we were just talking about in that last lecture about volumes of solids of revolution. I've got a different approach for us in this lecture. It's called the method of using shells. And it's different than doing disks because disks are like slices. Okay? Slices have to be perpendicular to the axis of rotation. Whichever way your solid is rotating is also the plane in which you want to slice. Okay, so shells is different. Whatever way you're rotating, it's like taking a layer that's wrapped around the center of that and being able to expand and contract to different sizes around that axis of rotation. So it's like taking peeling a layer off one piece at a time. And of course, depending on your shapes, these peels don't have to all be the same height, and they're not going to be the same diameter. Because what's happening, like I just said, is you're taking that axis of rotation and you're finding a circular peel around that center axis. Okay, so look, for example, right here, if I have this parabola, y equals x squared, and I want to rotate it around the y-axis there, it would make like this cup shape that's round at the bottom here and open at the top. If I were going to do this by discs, I would slice this way. And that would just give me disc after disc after disc that would sit there and expand all the way to the top. That's not what shells does. Since my axis of rotation is this way, my shell of rotation is parallel. Discs is perpendicular to the axis of rotation. Shells is parallel to the axis of rotation. So here's what's happening. My axis of rotation here around this y-axis. I'm going to take a single x value, okay? And once I choose that x value, that's important. Once you choose because it's vertical right here, okay? The reason why I pick an x value. Once you choose a value that gives me a line that's parallel to the axis of rotation, okay, my axis of rotation is x equals 0. If I pick some other x value, okay, that's parallel to it like this, then basically I'm going to take that line, but make sure it fits within the region that I'm interested in. In other words, I'm not going to take this little piece of the line down here because that's not in the thing that's being revolved, the thing that's being rotated. I'm going to take the piece of the line that fits inside of my shape that I'm rotating. And that line itself is going to rotate around. Okay? Now, of course, when you take a single line like this and you rotate it around, you make a cylinder. Right? That's basically what's happening. One shell is a cylinder, but a hollow cylinder. It's just the wall of the cylinder, not the top, not the bottom, not the inside. Okay? But the way we do volumes is we do shell after shell after shell after shell after shell, like layers. They're basically one inside of the other, right? Shell fits around this one, then another one fits around that one, then another fits around that one, and they just keep expanding until they fill up the whole volume. Now, of course, that doesn't mean that they all are going to be the same height. For example, right here, if I were to shrink this shell inwards, in other words, bring the x closer to the center, notice the cylinder has to get a little skinnier, but it's also going to get taller because the curve is further down as I get closer in. Okay, so the shells is not just pick one size of cylinder and just expand it. No. It follows, the shape of the curve that you're rotating. So sometimes the cylinders might be really wide but a little shorter, or sometimes they might be really skinny and really tall. Okay, but the shells, these cylinders, are going to change shape as you expand outwards. And by the time you let all of these shells expand outwards, it will fill in the whole volume. Okay, so how does that work with integrals? Well, the thickness the thickness of this is 1 point. I'm picking a single X value, and that's going to give me a little piece of a line, a segment if you will, and that segment's going to get rotated around. The thickness of that segment, the thickness of this wall is a single point. So the thickness in this case is dx. Now I could also rotate a cylinder, this way, and then the thickness would be this way and it would be dy instead. So it still goes both ways on that front. Okay, but here's how we calculate the volume. I start by saying, okay, I'm just going to calculate the area of the surface of that cylinder. So you notice we're still doing areas of different little cuts, okay? But these are more like peels. These are more like layers, okay? And I'm going to do just the area of the surface of the wall of that cylinder, of that shell. The way we do that is you basically imagine cutting the shell, the cylinder, down one side and opening it up like this. So I cut the cylinder in my mind and open it up. The height of the cylinder is still h, but the round part is getting flattened out, but it's still the same length. Remember, the circumference of a circle is 2 times pi times the radius. So if I know the radius of the cylinder's top circle, or bottom circle, either way, then the length is going to be 2 times pi times the radius, the circumference of this circle. Because all I'm doing is I'm cutting it and opening it up. I'm not changing that length. I'm just straightening it out. So if I know the height and the radius of a particular shell, I can calculate the surface area of just the wall of that cylinder. Okay? Times the thickness, which is dx or dy, gives me a small peeling, a small shaving of the volume that fits inside the thing. So if I do this for a whole bunch of cylinders that fill in the volume, I integrate all of those cylinder surface areas and I'll get the complete volume inside of the shape. Okay? So recap. I'm going to pick some sort of x or y value, depending on whichever one will give me something parallel to the axis of the center of rotation. Okay? I'm going to find a little line segment and I'm going to rotate that line segment around. Okay? It's going to make a little cylinder. And then I can do the area of the wall of the cylinder by 2 pi r times h. The thickness is going to be dx or dy, whichever one matches my method of rotation. And then I'm just going to integrate that. So here's our formulas for doing volumes by shell. 2 pi times the radius function times the height function times whatever differential. Right? It could be dx or dy. Now when I say radius function and height function, remember all I'm doing is I'm finding a shell, a cylinder, and then I would just need to qualify which quantity represents the radius and which one represents the height. Okay? So I've got an example just like that one here. I've got the parabola y equals x squared. I've cut off the top at y equals 5. And so I've got this region trapped, and I want to rotate it around the y-axis, okay? So just for a moment, go take a look at what this really looks like. As you can see, this is the region that is going to be revolved, and this line represents a slicing, a choice in a value. We'll start on the left. When you choose an x value, it's going to create a revolved cylinder, and as you increase, notice the cylinder follows the edge of the curve there and fits inside of the region but rotates it around. when you add up the layers, all of these cylinder layers, it makes the complete volume that looks like this. When I pick any particular point, since I'm doing it around the y-axis, that's an x equals 0 line. That's an x line is the y-axis, right? Here's the y-axis. I want to rotate around it by being parallel to it, which means I need to pick an x value. When I pick an x value, just go ahead and put a point on your shape, and then just visually notice, where's the height of my cylinder? Well, it needs to fit inside of your region, right? So if my region, let's say I'll pick it here also, right here is my x value. My region, I'll put the point right here. The height of the cylinder has to fit inside of the region there. And then if I'm rotating it this way, then my radius would have to be towards the center of rotation. So this would be my radius right here, and this would be my height right here. So the easiest way to set this up, well, for me anyway, whenever I'd always do these, is I would find that X generic point and sort of just picture the little cylinder surface that's being rotated around. And the location of that point will help me understand which quantity is the radius of the rotation and which quantity is going to be the height of that cylinder. Okay, there at different times they could be, functions, both of them, or one of them might be just a number and one of them might be whatever. All right, so look really closely. You'll notice if I have this point, the radius from this center right here is basically just x, right? You see that? The radius r equals x, the distance from the axis out to the point. That's just x of the point. Now the height of my cylinder is not below my curve. My curve y equals x squared is right here. The height of the cylinder is between the cap and the curve. So just like when you do area between curves, right? If I'm doing the area between something, I have to do the higher value minus the lower value. So that's why my height is 5 minus x squared, because 5 is the cap, and then x squared is the curve below. And that would have happened no matter where I picked the point. You could have picked the point way down here. It would still be 5 minus x squared to stay inside of the region. So let's set up the volume, right? It's 2 pi integral of radius, that's x, and then the height, 5 minus x squared, dx. I'm starting at 0 because that's where my region of rotation begins. And I go all the way out until these intersect. See, they intersect right here? They intersect when x squared equals 5, because it's y equals 5, right? So that means it's the square root of 5 for x. That's the x value of where they intersect. Okay, so then I have this integral that will give me the volume that fits inside of this paraboloid, if you will, right? It's going to be a circular parabola, and we're doing the volume that fits inside of it. So I've got 2 pi. I'm going to distribute this in. So I've got 5x minus x cubed dx. And then I'm going to do that antiderivative. So 2 pi 5 over 2x squared minus 1/4 x to the 4th from 0 to square root of 5. Of course, if I plug in 0, it's 0. That's lovely. 2 pi times square root of 5 squared is 5. Times 5 over 2 is 25 over 2. Minus 1/4 times square root of 5 to the 4th. Now, square root of 5 times square root of 5 is 5. Square root of 5 times square root of 5 again is another 5. So 5 times 5 is 25, and that's 25 over 4. I notice I can pull out a 25. That's going to give me 50 pi, and then it's 1/2 minus 1/4. But that's just 2/4 minus 1/4. So I've got 50 pi over 4, which reduces to 25 pi over 2. Okay? Now, I'm hoping, and I know that you're probably thinking is, well, wait a minute, we already talked about how to do these kind of volumes. I could have just done this with disks, right? I could have sliced this way, and I could have done pi times the x squared times dy, right? We could have just done that. Certainly. Yes, you certainly could. And the integral that you get would certainly give you this exact same amount. If you set this up with disks, if I did this with disk method, I would get pi integral from 0 to 5 of x squared dy. Because x is the radius of the disk that you would slice. And of course, x squared is equal to y. So notice what you'd be doing is pi integral 0 to 5 y dy. And this integral, notice, would actually, even much quicker than the one we did, get you to this same result, 25 pi over 2, because you just have 1/2 with the y squared. The 5 would get squared, you get 25, the 1/2, 25 and a half in the pi would give you 25 pi over 2. Okay, so next question. If that one's faster, why did you show me all this? Well, it's not always faster to do disks. It is always good to have a variety of different methods. And there are even some disk setups that would be a nightmare to try and reduce the integral. Okay? This is a completely different way of setting up these volume integrals using these little cylinders and the surface area of these cylinders, these little layers, these shells, okay, that allows me to have something that's parallel to the axis of rotation, whereas the disks would be perpendicular to the axis of rotation, right? Notice with the disks I had to do dy, whereas with the shells I was able to do dx, and sometimes that might make a difference. Maybe your function that you get, like y equals x squared, but maybe it's y equals something more complicated that I can't reverse solve. Like right here I was able to easily reverse solve and find the y, but if there's some function here that's too difficult to find an inverse of, then you may not be able to do a disk method for that one, right? You may have to do shells. It's important to know this other method, okay? So let's get several more examples of doing these solids by shells. For the first real example here, let's get a comparison between the new shell method that we were just describing and the old disk method that we were using last lecture. Both are very good methods, and at different times, either one could be shorter or longer than the other one. There are just certain situations that are suited for each one, and there are quite a few of them that can be done both ways. So it's really, up to chooser's poison, if you will, right? Okay, so let's do the new shells first, and then we'll compare it to the old disk method afterwards. We're going to have the region y equals x squared plus 4, x equals 0, x equals 2, and y equals 0. Okay, so x squared plus 4 is this parabola here. X equals 0 is the y-axis. Y equals 0 is the x-axis. So the only other piece that I need here is the x equals 2, which we'll put here. Right? X equals 2. So then, where does that meet over here? That's important. If x is 2, 2 squared is 4, 4 plus 4 is 8. Okay, it wants us to talk about the region that's inside of all of these curves. So that's going to be this region here. Alrighty. So if we're doing the shells, remember what I need to think about is I need to think about picking a value on an axis that's going to give me a line that's parallel to the rotation axis. Okay? So we're revolving around the y-axis. Here's the y-axis right here. In other words, I want to pick a line somewhere like this that's going to be parallel to this rotational axis. I'm spinning the shape this way. Okay? So I'm going to want to pick something that's parallel to that, which means I'm going to want to cut into my region like this. Okay? This is what one cut is going to look like into that region. And then, of course, I'm going to want to slide it all the way around this region, all the way from the left to all the way to the right. Okay, so when I do pick this, I'm picking some x value, as you can see, which means my thickness is going to be dx, right? It's along the x-axis. And when I pick this point right here up onto the curve, I can now talk about my rotation, okay? So my shell is going to rotate this way, which means something like this, something like this, like this. Okay, so my shell is going to be this surface coming out of the board at us right here. This cylinder right here, that I take this line that I chose and I'm going to rotate it this way. Okay? So before we get too deep in, go take a look at what shape this is gonna make when I take this region and revolve it, and what it looks like to have the different shells expanding from left to right. Just take note of how the side of the shell always fits inside of the region, and how when you bring all the shells together, it'll give you the whole solid that I'm going to show you. Okay, so here's this region. When you revolve this one, it gives you this solid piece. When you revolve it, you get this kind of empty cup-ish through the top and solid through the bottom. And the way the shells work on this one is from the left it gives you small, to the right it gives you larger and larger cylinders like this. And you can notice that the cylinders just follow the curve there. So let's do the calculation here. I just need a radius of the cylinder and I need a height. Well, you'll notice that from the point that I picked right here, this is the point right here that we picked, the radius from the center, that's going to be this distance here. The radius is just x, okay? Because it's the distance from the y-axis out to the point that we chose. That's just a x distance. And the height is going to be the distance from the x-axis up to the curve, which happens to be y. So for my shell's integral, my volume is going to be equal to 2 pi times the integral of the radius times the height times the thickness. Remember we said the thickness here was dx. Okay, now since it's dx, my two numbers on either side on the limits of my integral have to be x values. Well, we're going along the blue region here, right? That starts right here at 0 and ends at x equals 2. So I've got x equals 0 to x equals 2. And I'm almost ready to integrate. Y was my height, okay? But I need to actually make that into something involving x, because dx is my integral controller here. So volume is 2 pi times the integral from 0 to 2, x times x squared plus 4 dx. Because that's what y is equal to in this function here that we've drawn the point at, right? That's this distance. So I will distribute. That'll give me x cubed plus 4x dx. And then I will do the antiderivative here, which is going to give me 2 pi times 1/4 x to the 4th plus 2x squared from 0 to 2. Plugging in 0 is futile here. Doesn't give me any value. But when I plug in 2, I get 16 over 4 and 4 times 2. So that's 12 times 2 pi, a total of 24 pi. Okay? The real hump, the real hurdle to shell method is getting that setup going for the volume integral. But just like all the rest, once you've got that integral, a couple of antiderivatives and you're rocking and rolling. Okay, so let's show how doing it the old way with the disk method would actually give the same value. So let's draw the region again. I just need my x equals 2 line right here. And of course, my region is this same region here. And I'm revolving it around the y-axis, just like we just did, right? So the shape is going to look the same. The actual volume that I'm computing, the object is going to look the same as the one you just saw. The difference is how I'm slicing it. If I'm going to do it with disks, then my slice is going to be perpendicular to the axis of rotation. So I'll have a slice right here. And my slice is just going to be a circle. So I'm picking some y value. My thickness is dy. And then I'm just stacking these things up. Well, hold on a minute. Be careful. There's actually two different regions here. When you're going to do this one by disks, I actually have to do two different integrals. And that is because I have two different left-sided curves and only one right-sided curve. So look, if I'm picking anything between y equals 0 to y equals 4, I'm literally going from axis to line, axis to line, axis to line. That's all of these. All of these are axis to line, you notice that. That's one integral by itself because that's one type of pattern. But as soon as I go above y equals 4, I have to go from the parabola to the line, parabola to line, parabola to line. That's different pattern, okay? So one of them has a certain radius, the other has a different pattern of the radius. And I'm integrating with dy, so I'll need some y numbers. Remember this intersection we calculated a second ago was at 8. So here's how you would have to do this one by discs. I would have to say that my volume is equal to pi. Remember, discs is pi r squared because it's just the area of the disc. Integral from 0 to 4, that's just the bottom part. It's going from wall to wall, axis to line. Okay? That's a constant radius. The distance from this axis out to that line is always 2. So it's just 2 squared dy. That part's easy. Plus pi times the integral from 4 up to 8. That's the other part. That's going to be the region that I'm rotating in here. It's going to be the little sharp point of the top of this cup-looking thing. And the radius there is slightly different. Also, you got to notice that that's a washer, not a disc. Look, there's a gap between the thing that I'm rotating out here and the center of rotation. Since there's a gap, I technically have to draw the donut, the washer, where I'm going to be integrating all of the stuff in between. So that means for the top region, for this integral, I've got to do the washer setup, which is big R squared minus little r squared. Big R squared is going to be the distance from the center on out to the edge. Big R is going to be 2. Little r is going to be the distance from the center out to the curve. So little r is going to be your x distance from the axis to the curve. So that's going to be 2 squared minus x squared dy. Again, the thickness is dy. And of course, I can't leave x with a dy, but I do remember that my function here was y equals x squared plus 4. That tells me that x squared is equal to y minus 4. That makes it a bit simpler. So this whole x squared right here I can replace. All right, so I'll do this one real quick. This is an easy integral of just 4 times 4. That's going to give me 16 pi. Because there's no variables, right? It's just the length times the width on that one, times pi. Plus pi integral from 4 to 8. I've got 4 minus, now x squared is equal to y minus 4 dy. So I substitute that in, and this negative is going to distribute. So what I've really got is negative y, and I've got 4 plus 4. Okay, so 16 pi plus pi integral from 4 to 8, and I have 8 minus y dy. Okay, so 16 pi plus pi times the antiderivative portion, which is going to be 8y minus 1/2 y squared from 4 to 8. I'm going to have to plug in both. So 16 pi plus pi times 8 times 8 is 64. 8 squared is 64 times 1/2 is minus 32. 4 times 8 is 32, but remember it's minus bottom, so I have a minus 32 again. And then 4 squared is 16 times 1/2 is 8, but it's minus. It's on the bottom half. So double negative will give me a plus 8 on that one. Notice 64 minus 64, right? These are going to zero out. And I'm left with 8 pi plus 16 pi for a total of 24 pi, just like before. Okay, so the tables were turned a bit on this one. I had to not only split the discs into 2 integrals, but one of them was washers and the other one was discs. and it made it a little difficult to set up the inner and outer radii on that one. Whereas the shells in this particular method set up really clearly, quickly, and was able to get through faster. So it really just depends on the setup. Sometimes shells will be faster and easier. Sometimes discs and washers will be faster and easier. So you really just need to be familiar with both. So now that we've established shells is worthwhile, let's practice a couple of more examples of doing shells in the vertical direction. So I've got a region here, y equals x squared, and y equals 4x minus x squared. So it'll be a region trapped between those two. And we want to revolve this region around the line x equals -1. So let's draw it out first. Always helpful. Y equals x squared, parabola. We like those parabolas, don't we? Yep. And then I've also got the other parabola, which is 4x minus x squared. Okay, so if you notice what that is I can factor that out into 4 minus x times x, which means it'll have a 0 at x equals 0, and it will have a 0 at x equals 4. So I'm just going to have some sort of parabola, right, like this. Whoops. That hits at 4 over here. And what we're interested in is this region in between them, right? The region that's trapped between those two curves. Okay, well, of course, it would be important to figure out where these two intersect. So I'd have to set them equal to each other to figure that out. Let's do that. X squared is equal to 4x minus x squared. If I add the x squared and subtract the 4x, I'll have 2x squared minus 4x equals 0, which of course I can factor 2x, x minus 2. So you'll notice I'll have them intersecting at 0, which, as you can see, they do right here. And they'll also be intersecting at x equals 2. So that this point right here, in other words, is at x equals 2. I know my drawing's not to scale, it's a little bit lopsided there, but you get the idea. And we want to rotate it around the line x equals -1. Okay, so then x equals -1 is going to be somewhere over here. And I want to rotate this region this way, around that line. Okay, so let's construct our shell and then go take a look at what that's supposed to look like. Okay, so I've got my center of rotation. It's a vertical line, which means I want to slice into my region vertically parallel with it, right? Because I'm doing shells. Once you set up that vertical decision, you'll know that, oh, this must be dx, because I'm going to be doing this. I'm going to be slicing into it like so, okay, which means I'm going to pick an x value, which means my thickness of my shell is going to be dx. I'm going to have to rotate it out here somewhere, about like that. My shell is going to look something like that. And of course, I'll just be doing the surface area of it like so. Okay. So that's what one shell of this thing would look like. And of course, as I move my x value left and right, I would get different little heights. The height is here, and it'll be different distance from the center of rotation. So as I slide my x this way, my cylinder will get skinnier, okay? But also it'll move down on this region and get a little shorter too. As I slide it to the right, my cylinder will get wider, but it'll get skinnier up here too. So it just depends on the way that the curves are lining up, right? It's always going to be this piece, this line, being rotated around and making a surface. And then all of those surfaces put together will make an interesting little cup region with a swirl looking inside. Okay? Go take a look at what that really looks like for a moment. So here's our two graphs, the region in between. And when you take this slice and rotate it around x equals -1 here, right, it rotates it this way. And of course, as you take slices along different parts of the region, the cylinders get shorter, wider, different shapes all the way around. And they eventually make this shape. It's the hollowed out bowl cup looking thing. Has a cool little round top to it. The inside, this is the inside right here. And that's the outside. And as you can see, the cylinders make up the entire volume in between the two. Let's set up the calculation and actually get the volume that's being created by taking this whole region and rotating it around that line. So once I pick my x value, I've got my distance between my two curves, which is going to be my height. Notice the height of the cylinder is actually the line segment connecting the two curves there. Okay, so my height from here to here is going to be the top curve minus the bottom curve. The top curve happens to be the 4x minus x squared minus the bottom curve, so minus x squared. This is going to be the height of my cylinder. Next, my radius of the cylinder, well, here's the center right here. This is the center of rotation. So the distance from here out to here is going to be my radius. Okay? Now, the distance from the axis out to the curves is a distance of x. However, I also need to consider that it's not just from the axis, it's actually one more over from there. Okay? So then my radius, I'm going to move it down a little bit so you can see it better. My radius is this distance from here to here. Okay? The distance from here to here is just x. And the distance from here to here is always 1. Okay? So as you can tell, my radius is going to end up being x plus 1. Another way of thinking of it is that I have higher minus lower. X minus -1 is x plus 1. Okay? So from here, my radius is x plus 1. Because whatever the x value is, right, whatever x value you pick, it's that distance from the axis. And then I've always got the distance from the axis to the center of rotation is just one more than that. Okay, so we're ready, right? We know where the region starts at 0 for the x's, and we know the region ends at 2 for the x's. My thickness is dx. I've got a radius and a height of all of my cylinders. So my volume is going to be 2 pi integral from 0 to 2 radius times height. dx times thickness. So I just need to be able to perform this integral right here. I'm just going to multiply it out and do all my power rules, right? That's the quickest and cheapest way to do this one. So 2 pi integral from 0 to 2. I'm going to have x times 4x is 4x squared. I'm also going to have a minus 2x squared. So I'll go ahead and do 4 minus 2 is 2. I've got x times negative 2x squared is going to be negative 3x. Oh, I'm crazy. Negative 2x cubed. Right? That's x times negative 2x squared. And then I've also got 1 times 4x, which is 4x dx. Okay, double check. I've got the negative 2x cubed. I've got the 4x. I've got negative 2x squared and plus 4x squared, which gave me a total of 2x squared. Okie dokie. Now I am going to do the antiderivatives. So 2 pi times 2 over 3x to the 3, 1/2 x to the 4th, because that's 2 over 4, plus 2x squared from 0 to 2. Lucky us, again, we've got our nice little 0 that we can knock out because everything's going to zero out when I plug that in. And I can just start plugging in my 2 here. So I've got 2 cubed, which is 8. 8 times 2/3 is going to give me 16/3. 2 to the 4th is 16 times 1/2 is 8, so minus 8. And 2 squared is 4 times 2 is also 8, so plus 8. Well, that's a nice how do you do, right? Minus 8 plus 8. We're going to add the 0, leaving me with a total of 32 pi over 3 for my volume there. The next example here is something with a radical thrown in. Thought we'd have a little fun with a radical. And also a gapped region. One thing I hoped you notice on the last one and on this one is that if we were to do either of these with discs, it would actually be washers because there was an actual gap between the boundary and the center of rotation. So if you were going to do discs, they would actually be washers. Same thing is going to end up with this one. Let's graph this one out. I've got the curve y equals cube root of x. That looks like this. Then I have y equals 0, which is the x-axis. Already drew that, right? And we have x equals 8. So let's just slice it in there like this. X equals 8. Okay, so that's my region. That's this guy right here, right? That's this region. Nice. We're going to revolve it around x equals 10. So in other words, I need to have another line right over here next to the x equals 8. And that's my center of rotation. So then, if since I'm doing shells, I need to look at the fact that the center of rotation is vertical. So I'm going to cut into my region vertically. It's parallel. Okay, so I've got my cut this way, like so. And then I'm going to rotate my shell around this center here. So like this. And then of course this is the surface that I'm interested in. Okay. As I slide from left to right inside of the region starts at 0, it ends at 8. As I move my piece of line, my segment, left and right in there, my cylinder gets wider or skinnier. And as you move to the right, you can tell it will start to get a little taller, right? This thing does happen to do that. And as you slide it more to the left, it'll get really, really short and wide away from the center of rotation there. Go take a look real quick. Okay, so here's our region. There's our slice that we can move throughout the region there. We're going to be rotating this region around the x equals 10 line, which will give us this kind of solid right here. Notice there is a hole there. Since our region stops at 8 and we're rotating around 10, there will be a gap, a hollowed out centerpiece to this. We're going to be using the cylinders method, the shells method. So if I start really all the way at the right end there, there's my beginning inner shell there for the rotation. And notice as I move further to the left, we get all of the different layers. And also, as the x value moves to the left, you can see the cylinders do in fact get shorter if we move to the left. Okay, now let's calculate the volume using the shells here. Since we've picked our point, right? We've picked our x value here. You can already tell the thickness is going to be dx, right? That's the thickness of the line that I've chosen to rotate around the center there. The height is just the distance from here to the axis, right? This is my height right here, from here to here. Well, that height just happens to be the y value of the function, right? My height is just the y value. Okay, where's my radius? My radius is going to come from this point that I'm rotating, right? That's the point I'm rotating, to the center. So the distance from here to here is going to be the radius. So let's think about that for a second. If I pick this point right here, where's x? X is going to be the distance from the axis to the point. So in other words, x is going to be the distance from here to here. This is x. That's true for any point. If I go from the axis to the point, the horizontal distance is the x coordinate of the point. Okay? Now what's the distance from the axis to that line? It's always 10, because it's x equals 10. So the distance from here to here is 10 always. And I'm interested in this little piece of it here. So my radius would have to be the full 10, take away whatever x is. Because notice the distance from, like I said, from here to here is a full 10 from here to here. But then I always want just this piece, so I have to take away the x portion of it. Or if you want, higher minus lower, right minus left. The right line is 10, the left line is x, 10 minus x. Alrighty, so then let's set up our shells integral here. My volume is going to be equal to 2 pi times the integral from 0 to 8. Remember, these are x numbers, and I'm looking at the region itself. 0 to 8 are all of the lines that I can pick. Okay? Now, once I've picked a line, the radius is the 10 minus x. And the height is the y value, right, times dx. Now, of course, I can't leave the y variable in there. I'm trying to do it with a dx. So then this integral becomes 2 pi times the integral from 0 to 8, 10 minus x, and my y variable is equal to the cube root of x dx. Now, of course, instead of cube root, we would probably rather write this as x to the 1/3, right? But that's what my y variable is equal to. So I'm going to distribute that out and get some power rules out the way here. My volume is going to be equal to 2 pi integral from 0 to 8. I will have 10 x to the 1/3 minus 1 plus 1/3 is x to the 4/3 dx. Then this will be equal to 2 pi, and then my antiderivatives here. So 1/3 plus 1 is 4/3, which means I need to multiply by the reciprocal. So I'll have 10 times 3/4, or let me just go ahead and write that out. 10 times 3/4 x to the 4/3 minus 4/3 plus 1 is 7/3. So I'll have 3/7 x to the 7/3. And that's going to be from 0 to 8. Again, lucky us, the 0 knocks out, right? That's a nice thing to have in there. So then I'm left with my volume being equal to 2 pi times, if I plug in 8, I've got 8 to the 4/3, which cube root 8 is 2 to the 4th is 16, times 3/4 times 10. 16 times 3/4 is 12, times 10 is 120, minus 8 to the 7/3. Cube root of 8 is 2, to the 7th power is 128. 3/7 times 128. That is not going to be as nice of a number as we would have hoped, but we can still do it. We just need some common denominator stuff here. So I have 2 pi times some sevenths going on here. 120 times 7, that's going to be 840. And then right here, I just got 3 times the 128. So that's 360, and 24 is 384. Right? Okie dokie. So then 840 minus 384. I'll have 2 pi. I'm going to put the over 7 here because I'm just going to basically factor out the 7s there. Let's see. 10 minus 4 is 6. That would give me 13 minus 8, which is 5. And for a grand total of 7 minus 3 is 4. Double check me there. 10, 14, and yeah, okay, good. So then, let's see. 7 into this would leave me, nope, 7 doesn't go. So I just have to do 2 times this, which will give me 912 pi over 7. Okie dokie. So to finish up here, I want to talk about one that uses a dy now instead of a dx, just to have that full variety in there. We have the function y equals 8 over x squared, and the region trapped beneath that above y equals 0 and between x equals 1 and x equals 4. And we want to revolve that region around y equals 8. So let's draw a few lines in here. X equals 1 is going to be, somewhere about right here-ish. X equals 4 will be somewhere about right here-ish, give or take. And my region is trapped between the 8 over x squared and y equals 0, which is the curve here and, of course, the x-axis. So we are interested in this region right here. Okay. It is important to notice that I am going to get some intersection points here and here. On my y-axis, when x equals 1, I'm getting y equals 8. So this right here is y equals 8, right? Next, when I let x be 4, 8 over 16, right? 8 over 16 is going to be 1/2. So this intersection point right here is going to be y equal to 1/2. And that's sort of important too. I'm using shells, which means since my rotation is here, right? My rotation is around this line, y equals 8 here. I'm going to take some line in the region, right? That's parallel to that axis of revolution, and I'm going to rotate it this way. I'm going to rotate it this way, okay? Which means I need to talk about a slice right here. But I'm hoping that you're noticing that there's actually two different patterns. There's going to be the pattern where I take a slice up here when it'll be in between the x equals 1 and the curve. And then there's another one where the curve is no longer in the region. If I take a slice down here, if I take a cut into here, then it's in between the x equals 1 and x equals 4. What does that mean, Mr. Simon? Well, think about it. My pattern changes for the height of my cylinders here, the height of my things that I'm rotating. If I'm just going to rotate this guy right here, okay, then it's just going to do this and just be this guy right here, okay? And then as I slide up and down this thing, the length is going to increase depending on the size of the distance to the curve. But after I pass this intersection point, it's constantly in between these two lines. And those two lines are never moving. So it's this constant height between these two all the way down. So if I were to pick, say, a point down here instead, then my rotation would be way up here, right? And way down here. But it's going to be the same height every time for the ones in this second region right here. Okay, so I've actually got two different regions with two different height measurements there. Okay, so I've got to set up two different integrals. I'm going to set up the bottom one first. Notice that being parallel, okay, and before we get to much of the setup, let's take a look, right? But notice that being in the bottom portion and in the top portion right here, I have to be parallel to this rotation, right? Like this. That's going to cause me to use dy, okay? Because when I pick a y value to make this cut, right? The thickness is going to be dy. So go take a look real quick at the way this looks in the actual graph, and you'll see that it's two separate patterns whenever the cylinders get from one to the other. Okay, so here's our region that we graphed, and these are the directions that I would be cutting my shells into the region. It has to be parallel to the line of rotation, and our rotation line was at y equals 8 up here. So all of our slices here, you'll notice, are parallel to that. So my cylinders are going to be like this. They're going to extend down to the bottom there. Just notice for just a second that for this little small region, there's a little small part of the region here where you'll notice the cylinder never changes height until it hits that intersection, right? See that little snippet right there? It only jumps to where it's changing height after I get past that little straight line part right here, after it passes up this, and then it starts changing the height of the cylinder. Okay, so then here's my cylinder that's actually being formed, and as you can see, as we move the line further up the y values, the cylinders get closer to the center of rotation there at 8 until they're right on top of it, and the height of the cylinders keep getting less the higher the y value you go, right? You can see the higher the y value, right? It's getting to be a much skinnier cylinder there. After we're done adding up all of the cylinders, the solid looks like this. And what I've done is I've highlighted the very top and the very bottom of the solid. The bottom is red, so is this very top. And so you can see there's actually this little flat piece. That's the region right there that was the separate integral, or will be a separate integral. Right, it's that little piece in between there. Take a look. The volume that's in between, you see how I can fit my little region inside? That's the thing that's actually being rotated, and taking off the wall of the bowl here, you can see the volume of what we're calculating is what's in between here. So then what I'm finding the volume of is inside of this solid. And then you can see that the top here has this flat part. So as you see, the cylinders fit directly in there all the way to the outside, right? Doing all of those layers is what's going to make up that volume. Let's do the calculation here. The calculation, I'm going to have to split into two integrals. Okay, so I'm going to have my volume is equal to 2 pi, and I'm going to have the integral from 0 to 1/2. Now that's just this little region here. Okay, this little region here, I'm going to have the radius, which is going to be the distance from this point up to here, right? It's going to be this piece right here. Okay, except this part right here, the height to y equals 8 from the x-axis, right? From here to here is always 8. Not this. That's this curve. Y equals 8 over x squared there. The height from here to here is always 8. But what I need is a radius from the center of rotation out to this point that we've picked here. So I'll use big R for that one. Big R is going to be the 8 minus the y height that we've chosen. Okay, we've chosen a particular y height, right? It's going to go from 0 up to a half. So I've got 8 minus y is my height. I'm sorry, is my radius. Now the height of the cylinder, right? Turn your head sideways right here. The height of the cylinder is just going to be this length. But notice it's always between 1 and 4. At every slice in this region, it's from line to line, line to line, line to line. So from 1 to 4, that's just going to be times 3 dy. Straight up just like that, right? Plus 2 pi, and now I've got to do the integral of the rest, the 1/2 up to the 8. Why 8? Is it because that's the center? No. Go back to our original region here that we picked. That region was in between the lines right here and the curve itself. So I'm doing this region right here above that y equals 1/2 line. That's this region. And it just so happened that x equals 1 intersects the graph at y equals 8. So it's a coincidence that I'm getting it up to the 8 there. That just happens to be the intersection point. Okay? So I'm integrating from the 1/2 up to the 8 because that's this region. And I'm doing all of my y values, my slices. Okay? My radius is really the same thing. Look at it. Whatever y value I've chosen, okay, it has to be the top minus the bottom here. It's going to be 8 minus y. But now that I've passed up this intersection point, notice my radius is not going to be this constant 3 like it was for this little region. It's going to start to shrink. My radius is going to start to decrease as I get closer to this point. So it's going to be from the curve, which is y equals 8 over x squared, down to x equals 1. Okay? In its current form, I have a y equals 8 over x squared. That's not going to help me out. I need to convert it because it needs to be something in terms of x equals to be able to do a distance to the x equals 1. I need the height of the thing, which is from here to here. Okay? So I need this y equals 8 over x squared. I need that in terms of x. I'm going to multiply by x squared. I'm going to divide by y. I'm going to square root both sides. Like this. So now this is what represents my actual function curve here. And I am going to use this as my higher value. And 1, x equals 1, is the lower value. So it's this x value minus this x value, which gives me the distance between these two. So then my height over here is square root of 8 over y minus 1 dy. Like that. I just want to point out that if you had done this one with washers and sliced it this way, the integrals would probably be simpler. This is one of those situations. But we're practicing shells. So let's do our integrals now that we've set up our shell integrals here. Okay, so v is equal to, I can pull the 3 out. That'll give me 6 pi. Antiderivative is just going to be 8y minus 1/2 y squared. And that's from 0 to 1/2. Nicely, the 0 will go away. And I'll just be able to plug in the 1/2. So I have 6 pi times 8 times 1/2 is 4. And then this is going to be 1/2 times 1/2 times 1/2. So minus 1/8, like that. Let's see. 4 is 32 over 8. So that's going to give me 31 over 8. 6 pi times 31 over 8. The 6 and the 8 can reduce to 3 over 4. And 3 times 31 is going to give me 93 pi over 4 for that. Okay, so I've got that part done, right? From here on out, there'll be just a bunch of plus signs in between them as I go. 2 pi integral. I need to multiply out this yummy piece of yumminess here. Okay, now also in the process, I'm going to be converting things into numbered exponents so that I can easily do my antiderivative. Okay, so I have 8 times square root of 8, and that's y to the negative 1/2. Because there were no y's, and y is already in the denominator, and it's in a square root. So that's the first multiplication. 8 times negative 1, I have minus 8. Y times the square root of 8 over y. Let me on the side talk about that multiplication just so that you can be clear on the algebra there. Y times the square root of 8 over y is the same thing as y over y to the 1/2 times the square root of 8. Make sure you're with me on that one. I just took the square root with the y. And whenever you're dividing, right, you do top power minus bottom power. So this is just going to be the square root of 8 y to the 1/2. That's this multiplication, so I have minus square root of 8 y to the 1/2. And then negative y times negative 1 plus y. And then I have my dy there. Okie dokie. 2 pi antiderivative. This is going to give me y to the 1/2. And when I divide by 1/2, it's going to be times 2. So that's 16 square root of 8 y to the 1/2. That's always yummy, isn't it? Minus 8y minus square root of 8. That's going to be y to the 3/2, which is going to give me a 2/3 to go along with it. Right? 2/3 when I divide by the 3/2. And then lastly, 1/2 y squared. And that's going to be from 1/2 up to 8. Ooh, that's a yummy one. Yummy, yummy, yummy. Okay, so let's start by plugging in 8. 2 pi. I'm going to have square root of 8 times square root of 8, right? That's going to be 8 times 16. That's 64 times 2 is 128. Next, 8 times 8, that's minus 64. Next, 8 to the 3/2. Okay. So let me pull another quick algebra out here. I'm going to have 8 to the 3/2. So 2/3. 8 to the 1/2 is the square root of 8 that's already here. And then 8 to the 3/2. I just needed you to see that the square root of 8 being the 1/2 power, and then I have 8 to the 3/2, is going to give me 8 to the 4/2 total. Okay? So I'm going to have 2/3 times 8 squared when I do that, because 4/2 is just 2. Alrighty, so that gives me 128 over 3, because that's 64 times 2. So plus 128 over 3 plus 1/2 of 8 squared, that's 32. Nice. Minus, And here comes the fun part. I'm going to have 16 square root of 8, and then I have square root of 1/2. So bear with me, that's 16 square root of 8 over square root of 2. Make sure you're with me because that's square root, and I'm plugging in the 1/2. Square root of 1/2 is square root of 1 over square root of 2. So I just get this stuff over square root of 2. But that's going to reduce nicely because the 8 over 2 is, since they're both in radicals, it's going to give me a 4. Square root of 4 I can do. So that's a nice and easy simplification. Next, 8 times 1/2, I'm going to have -4. Next, I have 1/2 to the 3/2 power. And then times the square root of 8 over 3. So let's go through the algebra on that one as well. I've got 2/3. The square root of 8 is actually 2 cubed to the 1/2. Think about this. 8 is 2 cubed, and it's a square root, which is a 1/2 power. So that's 2 to the 3/2, and I haven't done this bit yet. Then I have 1/2 to the 3/2. It may not seem like it, but that works out really nice because what I'm going to have is 2 to the 3/2 over 2 to the 3/2, okay? Which is just going to be 1, and that's going to end up as a 2/3. Okay, so when I plug in the half here, I've got minus 2/3. And then 1/2 squared, of course, is 1/4 times 1/2 is 1/8. All right. So I've got 64 plus 32 is 96. So I've got 2 pi times 96 plus 128 over 3 minus, now bear with me, square root of 8 over square root of 2 is a square root of 4, which is 2 times 16, so minus 32. Minus 4, so plus 4. Minus, so plus 2/3. Of course, minus the 1/8. Okay, let's double check in there. So I've got grand total. I've got 93/4 times pi plus 2 pi times. This is going to give me 64 here again. Plus 4 is 68. Plus, I'm going to have a total 130 over 3. And then I've still got the minus 1/8 there. Ooh, yummy. Which is going to be equal to 737 pi over 3. All right, after I add those two together, a common denominator of 24 reduces to a denominator of 12, which of course I can wipe out times 3 here and add those for a grand total of 737 over 3. Okay? So I hope that this has helped you understand the other method that we use for volumes of revolution, shells. Most of them aren't quite this bad, but like I've always said, if you can get through the setup, the rest is mostly arithmetic. This one's kind of nasty just because of the radicals that were in there, right? So stay tuned for one more lecture. The next one we're going to talk about is one more application of integration, which is arc length and surface area revolution.